Hi everybody. This video is about Descartes' Rule of Signs. This is another really important theorem when dealing with polynomials. If you watched the last video on the rational zeros theorem, we ended up with a list of 32 numbers that were our candidates to be rational zeros of a polynomial. Well, if we'd like to narrow down that list, rather than checking every single one, there are a couple more theorems that can help us. And Descartes' Rule of Signs is one of those. Now this reads in a very awkward manner, but it actually says something pretty easy. So, suppose f of x is a polynomial written with descending powers of x. That just means you write it like you normally would. So we're going to take the first bullet and talk about that. If p denotes the number of variations of sine in the formula for f of x, then the number of positive real zeros, counting multiplicity, that's if you have repeated zeros, is one of the numbers p minus 2, p minus 4, ... Now, that seems really awkward. The most important part about that sentence is the number of variations of sine. So, let's take a specific example and see what Descartes tells us. So we're going to count capital P, the number of positive real zeros. Now, the theorem said that we should count the variations of sine of the formula. What that means is you go to the formula and you start with the first term. So the coefficient of the first term is negative 15. As you go to the second term, there's a change in sign. We went from negative to positive. So that's one sign change. Now do this again. We're going from positive to negative. So we have two sign changes. Then negative to positive. That's a third sign change. And then positive to negative again. 4 sign changes. So the number of positive real zeros might be 4. However, Descartes tells us just a little bit more than that. So let's check the statement of the theorem. Now you can still see my work, but I don't want to erase it. So the number of positive real zeros is one of the numbers, capital P, that we just calculated was 4, and then you're subtract 2, subtract 4, ... So what does that mean? Well, we start with 4. That's the number of sign variations we counted. And then you count down by 2. That's all that that ... was saying. Count down by 2. So 4 minus 2 is 2. Count down by 2 again. We get to 0. And we're going to stop when we get to 0. Why? Well, remember what we're doing. We're counting the number of positive real zeros. I'm going to stop when I get to either 0 or positive 1. It wouldn't make sense to go into negative numbers because we're literally counting something. We're counting the number of positive real zeros. Now, let's read the next bullet, and I'm going to try not to erase my work so we can compare everything. So the theorem says, we're looking at the second bullet point. If n denotes the number of variations of sine in the formula for f of negative x, then the number of negative real zeros is one of the numbers n minus 2, n minus 4. So we have this count down by 2 thing again. So this one's a little bit different. It's still the number of variations in sine. We're still counting down by 2, but in this case, you have to calculate f of negative x. So let's go back to our example and see what that's all about. So we have to calculate, or we have to write down, it's not really a calculation, we're going to write down f of negative x. Now, once you get comfortable with this, you won't really have to show this much work, but as this is an instructional video, I will show a little bit of work. So we're going to replace x with negative x. Just write down the whole thing. Like I said, once you get comfortable with it, you won't really have to write down the whole thing. Just replace x with negative x, plus 42, replace x with negative x, and then we have minus 8. Now, what happens with this polynomial If you have a negative raised to the fourth power, well, just pretend this is negative 1 times x. Negative 1 times negative 1 times negative 1 times negative 1 is positive 1. So negative x raised to the fourth power is positive x to the fourth. So this is negative 15 times positive x to the fourth. So this term stays negative 15 x to the fourth. However, when we get to the next term, we have negative x times negative x times negative x, because we're raising to the third power. Well, negative times negative times negative is still negative. So we have positive 50 times negative x cubed. So this is negative 50x cubed. Now go to the next term. Negative x times negative x is positive x squared, but positive x squared times negative 69 is negative 69x squared. Now the last couple of terms, there's not much to do. This is negative 42x minus 8. So that's f of negative x. And now we count, again, the variations in sine. So we start at the beginning term. Negative is still negative. Okay? Negative is still negative, no variations yet. Negative goes to negative, and negative goes to negative. So the number of negative real zeros, we did not count any variations in sine, so there are no negative real zeros. And here you can see why Descartes is kind of an important theorem. The number of positive real zeros could be 4, 2, or 0. But we know for a fact the number of negative real zeros is 0. So if we're doing this problem and we want to find all of the zeros, which is eventually going to be our goal, then I'm definitely going to start by checking the positive numbers. Now you might be saying, well, don't you know that all of the zeros are positive numbers? No, we can't say quite that much. Remember, there are these things called complex numbers, and this polynomial could have complex zeros as well as positive zeros. But still, we know there aren't any negative zeros. Anyway, long story short with Descartes' Rule of Signs, count the number of variations in sine, count down by 2, stop when you get to either 0 or 1, because it wouldn't make sense to count down after that. And the only real work is for the negative zeros. You do have to calculate f of negative x, but once you get comfortable looking at whether the exponent is even or odd, you don't really have to do a whole bunch of work here. Anyway, that's Descartes' Rule of Signs. Hope this helped.